everybody. This talk is called Making IPFS Work for You. If you can't see anything, sorry, apparently the bulb's a little iffy for the present here. Check out the live stream if you want the full colors. So, my name is Matt Ober. I am the CTO of Pinata, and we've learned a lot from running our platform over the past couple of years, and we're excited to share that knowledge with you. To start off with, a little bit about me, or the why I'm qualified to give this talk slide. I started off building Ethereum applications for about 2 years, a little custom enterprise stuff, and we noticed a lot of them were using IPFS, which kind of led us into Pinata. I've been working with IPFS for about 2 years since then, and this is my third ETHDenver, so I'm excited to be back and speaking this time. So, what is Pinata? Pinata is the solution for IPFS DevOps, as we like to say. If you don't want to manage all the IPFS infrastructure, or if you want added redundancy or speed for your IPFS-based product, come hit us up. It's easy, it's fast, and we make sure it's stable through our network of nodes around the world. So, we also have a $500 bounty this weekend for any hackers that are working with IPFS. Super easy. All you really need to do is just use our API. Looking forward to submissions. All right, on to the talk. So blockchains have a problem. They're really good at timestamping data, but they're really bad at timestamping a lot of data. It costs way too much to store any significant amount of data on chain. And for example, for something like Ethereum, it would cost thousands of dollars to store 1 single megabyte on chain. And that's clearly infeasible for many applications. So this has led to many projects storing data off-chain and then referencing where that data is stored on-chain. Uh-oh. Okay. So a common thing that we see a lot, an example that we would actually encourage people to avoid, is this pattern of referencing basically modern server URL-based infrastructure. So let's use our example here. Say you have an NFT or a non-fungible token on-chain. You want to store that data off-chain, but then you reference it with like a modern URL. So, myserver.com/thegrayscale pinata. All right, we can reference that back on-chain. But the problem with this paradigm is that we can change what that underlying image is without the end user knowing. This isn't very immutable, this isn't tamper-proof, and it's not very Web3. It's something that we're kind of looking to move away from. So, if we don't want to use the cloud to store our off-chain data, then what should we use? If anybody has a wild guess, the title of this talk is probably going to give this one away for you. So enter the Interplanetary File System, or IPFS for short. IPFS is what's called a content addressable file system, and it's what many blockchain projects are turning to for their off-chain data storage. So how does IPFS actually solve our blockchain data storage problems? Pretty simply. So how it works is you send data to IPFS, and IPFS runs it through some hashing algorithms and gives you back a unique hash, or what's called a content identifier. And then at any point in the future, you can ask the IPFS network and say, hey, can I get this content for this content identifier? And if somebody's still hosting that content, you're 100% guaranteed to get back what was initially uploaded. This is tamper-proof and immutable. It is exactly what we want when dealing with off-chain data. So, to give a little bit of an example of how this would work in real kind of application-based level, let's imagine we have a document and we send it to IPFS. IPFS gives us back that hash, and then we put that hash on something like, say, the Ethereum blockchain. Now, a user in the future, they want to grab that content. So they see on-chain, okay, here's the hash for the content that I'm looking to retrieve. They take that hash, and then they ask the IPFS network, hey, do you have the data that I'm looking for this hash? IPFS says, yep, here you go, and it gives it back to the user. The user's happy. So many of you are likely coming from a blockchain background, and it's why you're here today at ETHDenver. When working with IPFS, it's very important to know and remember that while IPFS is used by many blockchain products, it itself is not a blockchain. And this is most apparent in how the two technologies store their data. So with blockchain networks, when a user adds data, that data stays on-chain forever. That's because all of the nodes in the network are storing that data. And then if that user goes offline, users in the future can still pull that data from the network regardless of whether the original user is still online. Even if that original user is no longer connected to the network, the data is still there and can be retrieved. So with IPFS, this is not the case. In order for a user to retrieve data from IPFS, there needs to be a node that's online and hosting that data. So if the node hosting the data goes offline, the user that's wanting to retrieve that data cannot get that data because there's nobody to serve it. So the key thing to remember here is that the IPFS network does not actually store your data for you. It's not a magic cloud where everybody's kind of, working together to store your data for you, because that costs money, and that's not really, there's no incentive model to store data on IPFS. So if you want users to be able to retrieve your data, you have to have somebody storing that data. And it helps to think of IPFS in this regard to modern data storage solutions. So in a modern application, let's say you have your phone, you send data to your company server, and your server will send that to your database that you own somewhere. With IPFS, same sort of thing happens, except instead of sending it to a server, you're going to send it to either a company-owned IPFS node, or you could send it to a service that you pay to host that content for you. Cough, cough, Pinata. So the key takeaway here is that a node must always be hosting your content. Going to drive that point home. If you want your users to retrieve it, you got to have somebody hosting it, and they got to be online. So let's dive a little bit deeper. For those of you utilizing IPFS in your own projects, I'm curious if you ever run into this scenario. Your user uploads data, you store it on your company IPFS node, the user attempts to retrieve that data, and the gateway times out. And then now the user is sad because they can't find the data they're looking for. So this experience is relatively common with companies when they're first starting to work with IPFS. To understand why this is happening, we first need to understand how content is found on the IPFS network. Like we mentioned earlier, the IPFS protocol acts as one big routing layer for servers that are hosting content on the network. It's helping nodes announce and find content. So if you see in the diagram we have here, we have one node with the content, and it's constantly announcing to the network and saying, hey, I have this data, I have this data. This happens all the time. And then there's other nodes in the network. This is a common peer. Let's say the announcing node and the requesting node are both connected to. The common peer knows that our host node has the data, so then when the requesting node asks all of its friends, hey, does anybody know who has this data? Our common friend here knows who has it, knows to route the requesting node to the host node. So this is how content propagates throughout the network. However, IPFS has grown a lot lately. There's hundreds of thousands of nodes that are currently on the network, and currently, content discovery has started to feel a little bit more like this, where you have the host nodes are announcing their content, and you're shouting into the sea. Nobody knows where anything is because there's just too much noise. So this isn't great for user experience. So how can we avoid this congestion? Our first fix for this problem extends from what we're calling swarm connections. So IPFS nodes naturally connect and disconnect to other peers as they try to find nodes that are hosting content that they're looking for. However, if a requesting node asks their friends if they know who has this content, and the host node just happens to be one of those friends or those peers that they're asking, it's going to immediately respond back to the requesting node, hey, I have this content. This basically shortcuts around this lengthy lookup process that many nodes are going through on the public network. In practical terms, this means that the potentially long network discovery process is skipped, and the content can be served quickly. So key takeaway number 2 here. Connected nodes means fast content discovery. This is super important for any project that's building with IPFS. If it's taking a while for your content to be found, you need to make sure that the host node is connected to who's ever requested it. And there's a few strategies we can use for this. So how can we use this to our advantage? There's 2 main strategies. I talked about the first one a little bit, which is directly swarm connecting your nodes. This is like the easiest, kind of simplest way, the manual way to do things. And then the second method that we talk about is private or dedicated networks. And I'll explain what these are in a little bit. Each of these solutions has trade-offs, and one may be good for you, one may not be good for you. It just kind of depends on what you as an application are looking to build. So we talked about swarm connecting. Let's talk about how this works. Node A will manually connect to node B. And at this point, node A won't disconnect from node B. But node B doesn't care. Node B doesn't care about node A because it hasn't explicitly been told I care about node A. So as node B is garbage collecting, it may garbage collect the connection that node A established with it. So in order to prevent this, both nodes need to agree to connect to each other perpetually. So what we want to do is after we connect node A to node B, we need to tell node B to connect to node A. So it's this mutual process that avoids kind of nodes being taken advantage of maliciously, and ensures that if you want to stay connected, both parties have to agree. So with this connection, it lets applications create this fast lane between nodes that want to retrieve content and nodes that are serving content. So you have your requesting node and your host node, and they're kind of able to bypass this whole sea of nodes that are all shouting at each other. And again, fast content discovery. So let's talk a little bit about private networks. For some of you that are building on public platforms, this may not be the best solution for you. But for those of you that don't necessarily care if your content is retrievable via public gateways, it's a good option for performance. So how this works is that IPFS lets you make these things called private networks, where basically all the nodes in the network have to have a private key that they use to announce, hey, I have the permission to join this network. And in these networks, all nodes are only going to be connected to other nodes in that network. So you're not going to connect to the main IPFS network. And what this typically means is that there's going to be less nodes in the network. You're not going to, unless you have a huge application, you're probably not going to have hundreds of thousands of nodes that are all utilizing said private network. Maybe a couple hundred, maybe a couple thousand. Even still, that's very easily manageable by where IPFS is at right now. Which means a lot less noise and a lot quicker content discovery. So you don't actually need to manually swarm connect your nodes when you utilize a private network. All the nodes are just, by nature, going to be connected to most other nodes in the network. Similar regard, we're going to talk about what's called dedicated networks. This is kind of a marketing term that we came up with for private IPFS networks that you've exposed the private key for publicly. We didn't want to call them private open networks. That didn't seem fun, so we got dedicated networks. So it's similar in technical setup and benefits as the private network setup. But like I said, we publicly announce the key to get into this network. And what this means is that we kind of have a network shard. So if you are an application that is only dealing with data for your DAO or your scientific network or your music platform, whatever it is, you probably only care about data that's within your network. You don't want to deal with the DAO's data if you're trying to serve music files or content files. But you want to keep things a little sharded. So what we can do is announce that private key, and then just by nature, nodes aren't going to join that network unless they care about that data. So you kind of self-select your network into little tiny network shards. And the cool thing about this is that nodes can switch back to the public network at any time. IPFS is constantly getting better at content routing. It's constantly getting better at finding where and how to serve content. So if at any point in the future you want to switch back to the public network, you can. All you need to do is just get rid of that private key, flip a flag, and you're back on the public network, and all of your data that you've accumulated on this dedicated network is still going to be there. You haven't lost anything. The data's the same. The hashing algorithm's the same. It's pretty compatible, pretty easy to switch. So it's kind of a temporary stopgap solution that we recommend to some companies that are really experiencing load when using IPFS. So what this looks like in practice is we'll have something like the public IPFS network with all the gateways that are connected to it. And then you have little network shards that are technically private networks, but anybody can join them. So one for scientific data, a DAO, maybe a DEX, and then you can run multiple gateways on these networks as well. The cool thing about IPFS is anybody can run a node, anybody can run a gateway, and that's what makes it decentralized. You choose the data that you want to host, which is inherently centralized, but if multiple people are doing that and the access points for that data are decentralized, it's what helps kind of distribute the content, and that's what we encourage people to do. So in summary, let's compare. Swarm connecting, it's the simplest setup. Your nodes are still participating in the global IPFS network, but the speed improvements are only going to be realized by nodes that you manually connect to. It's a pretty manual process to set up, and it's less scalable. Private networks. More complex of a setup, and the network is private. It's only accessible by nodes in the network. So this is good if you don't want other people seeing your data and you also want speed improvements. It's a smaller network, which means faster content discovery for all network participants. And then lastly, dedicated networks. Again, a more complex setup is this is basically the same thing as a private network, but like I said, we've exposed our private key, so anybody can technically join it, but only people that really care about the data in that dedicated network are likely to join it, so it cuts down on the traffic. And then again, smaller network, faster content discovery for everybody involved. So thanks for listening to my talk. If you guys have any questions, feel free to reach out to us at Pinata. We'd love to help you with anything you're building.